Today we are covering lesson 5.2 on using perpendicular bisectors. This is the first lesson where we're focused on a specific trait of, say, perpendicular bisectors in a triangle, and then we'll kind of introduce how that would work if there were multiple perpendicular bisectors in a triangle. What's the importance of that, and maybe where they meet, getting into the centers of the triangle for today. So starting off, we are proving what perpendicular bisectors do. And in this theorem, CP is the perpendicular bisector of AB. And we're proving that the hypotenuse then will be congruent, right? Now, in this situation, right, we've got a term we haven't really used before in perpendicular bisector. It's going to give us both perpendicular, so get your right angle box drawn, and bisector, right? And again, we're talking about specifically bisecting the side. We can't be both perpendicular and cutting the angle in half, right? So we've got that information already on there. So I see side angle, potential for hypotenuse leg in this proof, right? So in those first two steps, we've got given something perpendicular bisector, we get perpendicular, and we get bisector, right? So we have both those pieces of information. Now I need to go back and look up. I see a reflexive. That tells me side angle side. So because of side angle side, we're going to use that these are angles congruent. So my next step is going to be those two angles, APC and BPC, are going to be congruent to each other because all right angles are congruent. Next up, we need the reflexive I already mentioned. CP is congruent to itself. And then we have the triangles are congruent. Side angle side, as stated earlier, and then that's going to lead us to the hypotenuse of these triangles are congruent. Even though we didn't use hypotenuse legs, because it's a right triangle, it is still hypotenuse. So then CA and BC are congruent, or CA and CB. There's kind of match here. This is one of the proofs where you want to know how to do, because many of the other proofs we get into are 7 and more steps, and so it's nice to kind of deal with the shortest amount of steps proof. So hint, hint, wink, wink, make sure you know how to do this proof. Moving on, we now have in a plane, if the point is on a perpendicular bisector, those hypotenuses are congruent. So given perpendicular bisector, the hypotenuses are congruent. Secondly, we've got the converse, which flips it. If we have any segment that happens to be congruent to the endpoints that my perpendicular bisector is on, then this point D must lie on the perpendicular bisector. So basically, we just need the congruent marks, and to know there's a perpendicular bisector, to know that the center point has to lie on that. Moving on. We have solve for MN. Now, generally speaking, what we just went over is we need to see perpendicular and bisector to know that the hypotenuses are congruent. So I see perpendicular, I see bisect, therefore these are going to be equal, so MN must also equal 2.6. Right? We got to check both of those off to get the conclusion. Next one is dealing with the converse. It says solve for BC. We've got 38 and 38, therefore this is a perpendicular bisector, so these must also be equal. So I have 12, but what is BC? Right, BC is here to here, so I've got two 12s, so 2 times 12 gives me 24 is the length of BC. If you ever run out of time to write some of the notes down, feel free to pause to make sure you get it all written down. BD is a perpendicular bisector of AC. Solve for X. Right, so if this is a perpendicular bisector, these must be congruent, and so you've got 5x, this 3x plus 14. Subtract the 3x from both sides to get 2x is 14, and x is 7. Now again, always double check that I just want x, because we could plug it back in to get AB, or CD, right? So just recognize that you may need to double check. You might have some homework that asked for what is CD, what is AD. And the next, WX is perpendicular bisector of YZ. What segment length in the diagram are equal? So perpendicular bisector says those are equal. Then these are hypotenuses, so they are congruent. So let's write them down. We got XY congruent to XZ. And we've got WY congruent to WZ. And I also see 25 and 25, so VY and VZ are also congruent. The next question says, is V on WX, right? Because it's a perpendicular bisector and these are congruent, you would say yes, it is on WX, right? Because those lengths are congruent, it must be. And again, say if you're not confident, you run into this on some sort of quiz or ACT or something. Make perpendicular congruent triangles if you can. Well, we've got hypotenuse leg here, so it must be that it is on that line. Right? Like if we connect that line, what do we have? Angle side to side, which means hypotenuse legs, and it is on there. Next up is now dealing with where do multiple perpendicular bisectors meet? When more than two lines meet at a point, they call that a point of concurrency. And if the lines all meet there, they'll call them concurrent lines, right? It's just a fancy word for intersection of more than two things. Now the perpendicular bisectors of a triangle intersect to form, to meet at a point that is equidistant from the vertices, right? Equidistant from the vertices. Now, just do one piece at a time, right? Where does this come from? This was a perpendicular bisector. Those are congruent, and so are the hypotenuses. If PF is a perpendicular bisector, then these are congruent, and the hypotenuses are equal. So all of those hypotenuses are equal, and we only got through two of them, okay? Like we didn't go to the third perpendicular bisector. So if we have perpendicular bisectors, then we're equidistant from the side. Now the term for this point, or point P, is called the circumcenter. Right? Where the perpendicular bisectors meet, it's called the circumcenter. Right? So we have a lot of terms in this chapter. That is the first one. Now going through the rest of this, it says the circumcenter, P is equidistant from the three vertices, so it makes P the center of a circle that passes through all three vertices. So like if this was P, you drew the circle such that P was the center. You would notice our vertices are all on the edge. Now there's also another kind of little thing to that. Then notice where is the circumcenter in relation to the triangle, right? Even though it's called circumcenter, in an acute triangle it's inside, but on a right triangle over here, it is on the triangle. It's not inside, it's on the hypotenuse. And even furthermore, out here the circumcenter is outside the triangle when it's obtuse. It's a little different, but type of triangle can kind of prohibit or affect where that circumcenter is going to appear. And now again, what are some uses of the circumcenter? Right here, right? Finding equal distance away from 3 points on a map, right? You could do that to make three people drive an equal distance to meet each other. And again, it would make probably more sense if you were much further away. If you're all, 300, 400 miles away or so, right, to find a middle point, not just like meeting in Rochester necessarily, but that's just kind of a situation that would make more sense. Also for police and fire jurisdiction, right, if you had three big monuments or big places in town, like say a stadium, maybe the mayor's house, and maybe you got a really fancy art place, then you would want the police to be able to respond to those in equal timing. You would want them to be, police station to be located at the circumcenter so it can equally get to those all at the same time. Same thing with like a fire station if you wanted to cover important spots. Next, solving for X and Y. So here's a tricky one. I'd say give yourself 30, 40 seconds, see if you can figure out how can you solve for X and Y when you have pieces that are equal to each other but have different variables. So go ahead, pause the video, and give yourself a chance to try that one out. So this equation, right, we've got perpendicular bisector, we've got a situation where x plus 1 equals y minus 5, and we have an equation where 3x minus 1 equals 2y minus 6. Both of these equations have a value that works for both x and y that give me, that makes the situation true. This is called a system of equations. Now, the easiest way to solve this is generally to pick a variable, solve for that variable so that once we solve, for example, solving for y in the top equation just involves adding 5 to both sides. X plus 6 equals y. Now that we have y equals x plus 6, this same y in the second equation has to also equal x plus 6. So when I substitute, right, where this y is, I get 3x minus 1, the left side of the equation stays the same, equals 2. Y now becomes x plus 6 minus 6, because there's still a minus 6 there. I can now solve because now we only have x's, and we can find what x is going to be. So distributing 2x plus 12 minus 6 becomes 2x plus 6 equals the 3x minus 1. Remove the 2x from both sides and plus 1 to both sides, and you get x equals 7. Some people will be like, finally, we're done, but that's wrong. Well, that's one answer. I need to use this x plus 6 again, knowing that now x is 7. We're going to plug 7 into where the x was to get what y is. 7 plus 6 is 13, so y is 13. And especially on these problems, it pays to double check. So double check, plug in 7 for my x's, plug in 13 for my y's, to double check that my answer still works. 7 plus 1 is 8. 13 minus 5 is 8, so those are still equal. That one worked. 21 minus 1 is 20. 26 minus 6 is also 20, so those also work. So my end answer was indeed x is 7 and y is 13. One last proof of the converse proof theorem is right here. We've got some information pre-labeled for us with the reflexive already in the picture, but this is kind of a different one, which is why I have it given to you here, right? Because look at what we're proving. Something is on the perpendicular bisector of a line, right? And so what we're going to do is we're going to be able to kind of assume perpendicular from the perpendicular postulate, right? So this one we don't use often. The perpendicular postulate says if there's a point not on the line, then there is exactly one line through that point that is perpendicular to the other line. So that's what we have here. So we're saying CP is perpendicular to AB. Now you might want to jump and say, okay, it's hypotenuse leg. However, we have some options. We also know that it's isosceles triangle, so we can use base angles, right? With base angles theorem, I've kind of got an angle side-side thing going, so that usually is hypotenuse leg. Or we could do angle side, right? So we're going to skip the reflexive this time and try angle side. So perpendicular postulate is going to give us, well, first for base angles theorem, sorry. So we got the angles congruent, and now we're going to use definition of perpendicular to give us right angles, right? We're calling them 1 and 2 this time for abbreviation. And then we've got closer congruent, okay? Because right angles are congruent. And now we got angle, the side given to us, so triangles are congruent by angle, side. Need my triangle mark here that erased. And then what's left? How can I say that CP is on the perpendicular bisector? We assume perpendicular, we need to grab bisector. AP and PB are congruent, and therefore that means we are on the perpendicular bisector. Because now we have that bisector piece, and CP is on the perpendicular bisector. Feel free to email if you have any questions. The homework is on Google Classroom.